Hey guys, in this video, I want to talk about stoichiometry. Okay, so let's just first define stoichiometry so that we have an idea what it is. So, stoichiometry is basically the relationship between relative quantities taking part in a reaction or forming a compound, typically in a ratio of whole integers. All right, and so in many ways, you could think about stoichiometry much like you're cooking. If you want to make, enough eggs for one person scrambled eggs for one person, you will use two eggs, for example, right? And so if that's the ratio that you use, well, if you're cooking for scrambled eggs for three individuals, then you will know that you need 2 times 3 eggs for those three individuals. So stoichiometry pretty much works the same way. It's with that ratio, that relationship between reactants and how much products they can produce, and vice versa. Okay, so let's talk about this generic reaction here. Okay, so we have 2A plus 3B yields 5C and 4D. Okay, so what you could say from this relationship, this chemical equation, so the chemical equation gives us the stoichiometric relationship. I can't really say the word. All right, so for example here, right? So what we could say here is that for every 2 moles of A, you'll produce 5 moles of C. How do we come up with that? Well, look at your chemical equation here. We have 2 moles of A will produce 5 moles of C. Okay? We could also say that 3 moles of B will produce 4 moles of D. Same idea. 3 moles of B will produce 4 moles of D. All right? We could also say that 2 moles of A reacts with 3 moles of B. So what I've given you here are just some stoichiometric relationships between the variables that we find in this chemical equation, but there are others, okay? So like, for example, there's 5 moles of C for every 4 moles of D that you produce, okay? You could even say that 4 moles of D is produced for every 2 moles of A that you use, okay? Regardless of the case here, this is the stoichiometric relationship that exists from this chemical reaction, all right? So as I said earlier, these are just some of the relationships or the stoichiometric relationship or the ratios that you have one to another, all right? And the ratios still exist even though you use multiples of the coefficient. So like for example, if you have 4 moles of A, okay, you also produced 10 moles of C. Well, how does this work? If you notice the relationship between this 4 moles of A and this right here, which is just 2 moles of A, if you notice, all I did was just multiply this by 2. All right, so if I multiply this by 2, then we must do the same thing for C. All right, and so we have 5 moles of C here in the original chemical equation, so we must multiply this by 2 in order to get 10. All right, so here are other examples that we could talk about. Let's say if we have 6 moles of B, okay, this will produce 8 moles of D. All right, so if you notice here, once again, I multiply this by 2, and so I will multiply this number by 2 as well. If we have, for example, 6 moles of A, all right, it will also react with 9 moles of B. So if you look at the relationship here between here and here, so I multiply this number by 3 to get 6, so I need to multiply this number by 3 as well to get 9 moles of B. Regardless, these are the ratios. So if you multiply, or if you, let's just say, triple this number, all right, to completely react, you gotta triple this number. All right, and then you will make triple this number and triple this number, all right, or 5 times more or 8 times more, even if you have it. Regardless, these are the basic relationships that you have. So what about if we use numbers that are not, clean or easy multiples, like the previous problems that we were just talking about? How would you do this? All right, and we'll still use the whole idea of dimensional analysis just to convert from one thing to another. So, like for example, if well, if 3 moles of A react, okay, how many moles of C are formed? Okay, so that's what we want to know. So we want to know. All right, so let's just kind of highlight our starting unit and our ending unit. So we start off with 3 moles of A, okay? And we're trying to figure out how many moles of C you make, okay? So once again, you need an equivalence statement. Where do we get that equivalence statement from? We will get the equivalence statement basically from this chemical equation here, all right? And you're looking at most specifically, you're looking at moles of A and moles of C and the relationships they have with one another. In this case, the relationship that exists, the equivalence statement that you see here, is that for every 2 moles of A, you produced 5 moles of C. All right? So if that is the case, then we could come up with our conversion factors. All right, so the conversion factors that you could possibly use for this problem is that 2 moles of A over 5 moles of C, or 5 moles of C over 2 moles of A. Okay, now let's just go ahead and answer this problem. So starting out with our beginning number, so we have 3 moles of A. We need to figure out which conversion factor we're going to use. We got to get rid of this moles of A. So which one we're going to use? Not this one, but this one, because of where this unit is. So we're going to write 5 moles of C over 2 moles of A. This way we could cross out moles of A. And then now we could just do the math. So 3 times 5 divided by 2. You plug this up in the calculator, and you should get 7.5 moles of C. And that's your answer for this problem. So for this next example, let's use a real chemical equation. All right, so in this case, we have N2, so nitrogen gas plus hydrogen gas, 3H2, yields 2NH3, which is ammonia. All right, and so let's answer this problem here. So if 0.052 moles of N2 are reacted, okay, how many moles, how many moles of NH3 are formed? Okay, so you're starting out with this many moles of N2, and you're trying to figure out this many moles of NH3. So we're going to use the equation to help us figure out what's our equivalence statement, how these two units are related to one another. And so when you notice, here's N2. So we see that for every 1 mole of N2, you make 2 moles of NH3. All right. And so we could go ahead and write this out, where we have 1 mole of N2 is equal to 2 moles of NH3, okay? If you need to write your conversion factors, go ahead and do that. So your conversion factors are for every 1 mole of N2 is over 2 moles of NH3, or for every 2 moles of NH3 is over 1 mole of N2. All right, and then we got to figure which conversion factor we're going to use for this problem. So in this problem here, we start off with 0.052 moles of N2 times, all right, so we need to get rid of moles of N2, and so that means it must be here in the denominator, All right, so the only one that's true is this one. So we'll copy this conversion down. All right, and so your answer, you cross out moles of N2, we're stuck with the units of moles of NH3, and so we'll multiply this through, and when we do that, your answer is 0.104 moles of NH3. And that's your answer for this particular problem. So here's another problem. New equation. So H2, 2H2 plus O2 yields 2H2O. So the question is, determine the number of moles of H2O produced when 5.2 grams of O2 are reacted. All right, so a couple of things that we need to highlight and to verify. So we're looking for moles of H2, but I'm starting you off with 5.2 grams of O2. All right, so this is really important here. And, depending on the units given to you, depends on how you do this calculation. Now, what you have to realize is that the coefficients here that are given to you in the chemical equations are always in moles. So before you could convert from one substance to the next, it must be in moles. So if I give you any unit other than moles, so like for example, this question here, any unit other than moles, so here I gave it to you in grams, you must convert that number to moles first, and then once converted to moles, then you could do the mole-mole conversion between one substance to the next. Now, why does this work? Because moles ratios are just numbers, all right? How many to how many? So for every two H2s, you make one O2s. Or for every 2 moles of H2s, you make 1 mole of O2. Or you react with 1 mole of O2. For every 2 dozens of H2 reacts with 1 dozen of O2. These ratios are always the same, okay? And so if you have something in grams or mass, you're just talking about its mass, how much it weighs. You're not talking about how many. And so you need to know the how many first. Okay, so for this problem, the very first thing I'm going to do is I need to convert this grams of O2 to moles of O2. All right, so 5.2 grams of O2. So to convert it from grams to moles, you need the molar mass, right? So we know that for every 1 mole of O2, so watching that this is O2, so there's 2 oxygens, all right, it's roughly 32 grams of O2, and that number we could take it straight off from the periodic table. By doing that, we could cancel out the grams, and you're stuck with moles, which we want, all right? Now, you could go ahead and calculate this, you get this number, and you move on, or we could just continue and just do the very next step. Now, the very next step is that you're trying to find the moles of H2O. So now that we know the moles of HOO2, we could go up here and look at the mole-mole ratio between the two. So we know that for every 1 mole of O2, based off of the chemical equation here, you have 2 moles of H2O. Okay, and so here is now your mathematical equation to answer this problem. So it's 5.2 divided by 32 times 2 divided by 1, and what you'll get is 0.325 moles of H2O, and that's the final answer for this problem. Okay, so let's look at another example. So how many water molecules are produced when 5.2 grams of O2 are reacted? So once again, highlight your unit so you know where you're coming from, where you're going to. We're trying to get to water molecules, and we're coming from 5.2 grams of O2. Now, I'm going to emphasize this point again. When you're looking at the chemical equation, for all stoichiometry problems, you need the chemical equation, but when you look at the chemical equation, these numbers here are in moles, all right? And so before you could compare one thing to another, it must be in moles. So whatever unit that's given to you first, if it's not in moles, you must convert it to moles first and then convert one to the next, all right? And so if you notice here, I start you off basically with grams of O2, and you need to go to water molecules. So this is kind of like a hefty question because you're doing a lot of converting one thing to another. So let's go ahead. Let's shoot this. Let's go for this. So we're going to start off with 5.2 grams of O2. We need to convert this to moles. So we know that 1 mole of O2, based off the periodic table using the molar mass, is 32 grams of O2. All right. So now that we converted to moles, now we could go convert from moles of O2 to moles of H2O because that's what we're trying to get. So we know that for every 1 mole of O2 gives us 2 moles of H2O. All right, but we're not done yet because we're trying to figure out how many water molecules. And we know to get to molecules or particle, we need Avogadro's number. And so the relationship we know about Avogadro's number is that for every 1 mole of H2O, there are 6.02 times 10 to the 23rd. So here, once again, we could cross out moles of H2O so that what you're left with, or the unit you're left with, is molecules of H2O. All right. And so now all we have to do is just plug in the math inside your calculator. And what we're going to have here is 5.2 divided by 32 times 2 times 6.02 times 10 to the 23. And when you plug this into the calculator correctly, you get 1.96 times 10 to the 23 molecules of H2O. All right, so here's one more example, last example of the day. All right, so how many liters of H2 are used when 5.2 grams of O2 are reacted at STP? Once again, highlight, make this a step of yours that you use all the time. Highlight the units that you're dealing with. So we're trying to figure out liters, all right? How many liters of H2 specifically, right? We need to know what substance we're talking about. Are used when you use or when you react it with 5.2 grams of O2, all right? So once again, if it's not in moles, you must convert it to moles. And only in when it's moles, then you could look at the mole-mole ratio of one substance to the next. All right, so in this case, we could look at the mole ratio of oxygen to H2. All right, so let's go ahead and let's just work through this math. So we started with 5.2 grams of O2, and we need to convert this to moles, all right? And so we're going to use the molar mass of O2, which like last time is 32 grams of O2, all right? And then now we have in moles of O2, we can convert from moles of O2 to moles of H2. And so we see that for every 1 mole of O2, there are 2 moles of H2, all right? Now that we have that, now we need to know how many liters we have of H2 at STP. And so we know that relationship is that for every 1 mole of H2, it has the volume at STP 22.4 liters. All right, and so everything should cancel out. So grams of O2 cancel out, moles of O2 cancel out, moles of H2 cancel out, and you should be left with liters of H2, which that's what you want. And so when you put this in your calculator, you have 5.2 divided by 32 times 2 times 22.4, and you should get the grand total of you should get the grand total of 7.28 liters of H2.